Welcome to another video from explainingcomputers.com. This time I'm going to focus on running a Raspberry Pi on batteries. Which Raspberry Pi, I hear you cry? Well, I'm going to be looking at a range of models from the Raspberry Pi Zero up to the Raspberry Pi 4. And I'm going to be using USB power banks to power the Pis, but also a larger 12-volt lead-acid battery with an associated converter. And of course, I'll be considering the issue of battery life expectancy. So, let's go and get started. Greetings! Here we have the 5 Raspberry Pis which are going to take part in this video. And specifically, we've got a Raspberry Pi 4 2GB model, a Raspberry Pi 3B Plus, an absolutely classic Pi, a Raspberry Pi 3A+, a much underrated Pi, a Raspberry Pi Zero to which I've soldered a GPIO header, and finally a Raspberry Pi Zero W, which is just like the Raspberry Pi Zero except it's got Wi-Fi and Bluetooth via this little shiny chip down here. And all of these boards require a 5-volt power supply, actually a 5.1 volt power supply, which can be connected either via a USB connector, via micro USB on most of these Pis, or USB-C on the Pi 4, or you can power them via their 5-volt and ground GPIO pins. Before we start testing these boards out on batteries, it will be useful to know their power consumption, and this will of course depend on what the Pis are doing, what applications they're running, and also what is connected to their GPIO pins and their USB ports. However, very helpfully as a guide, the Raspberry Pi Foundation provides this web page which indicates the typical bareboard active current consumption for all Pi models, as well as the maximum total USB peripheral current draw. And of course, I'll give you a link to this page in the video description. Anyway, what I thought we'd do is to take the typical bareboard active current consumption for the Pi models we've got here and to put the figures in the first row of a table. And with this done, let's go in search of a battery and see how long it can run each of our Raspberry Pis. Guess what? Here I've got a USB power bank, the kind of thing you might use to provide extra power for a smartphone or a camera. And specifically, this is a Belkin Pocket Power 10K, which is a 10,000 mAh unit that I recently purchased for £20, which is about $28. And batteries like this are potentially great for powering a Raspberry Pi, as they've got USB outputs. We've got 2 Type A USB outputs on this unit, as well as a micro USB input for charging the thing up. It is, however, worth noting that some USB power banks don't work well with single-board computers, as they cut off if the power draw is too low. And therefore, when selecting a USB power bank, you need to get one, if you want to use it with a Raspberry Pi, that is operated via a switch like we've got here. This one is turned on by pressing the unit there. It's not turned on automatically when you plug in a load. And that should allow the unit to work properly with a Raspberry Pi. It's also worth noting that you're going to need a power bank that has got an appropriate rating for the Pi you're using, and in theory that is 1.2 amps for a Pi Zero, 2.5 amps for a Pi 3A or Pi 3B, and 3 amps for a Pi 4. However, this Belkin unit is rated at 2.4 amps, and I've found this powers all Raspberry Pi models, including the Pi 4, with no problems. So you cry, how long will a 10,000 mAh battery like this power our Raspberry Pis? Well, in theory, we can just divide the capacity of the power bank in milliamp hours by the typical current consumption in milliamps for each Pi to get a figure in hours. However, in practice, the usable capacity of any rechargeable battery is less than its rated or notional capacity. And for the lithium polymer or lithium ion batteries we find in a USB power bank like this, usable capacity is typically about 75% of the rated capacity. So, if we return to our table, we can calculate that our 10,000 mAh power bank should run a bareboard Raspberry Pi 4 for 12.5 hours. This figure being obtained by dividing 10,000 by 600 and then multiplying by 0.75 based on a 75% usable capacity. Doing the same calculation for the other Pi models, we get up to a theoretical bareboard battery life of 75 hours running our Pi Zero on the 10,000 mAh power bank. And if you have a power bank of say 5,000 mAh capacity, it'll be half of this, and so on. Anyway, that's the theory, but what I want to do now are some practical battery tests. Right, here I am back again, and I've got the Pi 3A Plus all connected up and running. I thought we'd give it a starring role in this video, and if we go across to its desktop, you'll see I've written some Python code. And the idea here is to test the battery life of a Pi when it's running headlessly with a minimal load and just performing occasional activities, as would be the case if it was, for example, monitoring sensors, running something like the weather station I built on my channel earlier in 2021. So let's just look at what this code does. For a start, it imports some libraries, the time library, the GPIO library, and also the OpenPyXL library, which is a library in Python for working with spreadsheets. And before you can import this into a piece of code, you must have opened up a terminal and done a sudo pip install OpenPyXL to install the OpenPyXL library. Back in the code, I'm setting up GPIO to have GPIO pin 7 as an output, because as you might have noticed, I've taken an LED and soldered on a current limiting resistor and a header so I could put it on the Pi, and we can use this to monitor the Pi's activity whilst it's running the test. Next, down in the code, we're finding out start time. Start time as a variable is going to be set to time.time, which is the current time in seconds. And then we're going to load in a spreadsheet. And that spreadsheet is up here. It's a very simple spreadsheet. It's completely blank at the moment. But what we're going to be doing is across this test, writing the uptime of the Pi into the spreadsheet so that when the Pi runs out of battery power, we can look back at the spreadsheet and see how long the battery lasted. So back with the code, we're going to do that inside 3 loops. First of all, there's a while true loop, an infinite loop, which will keep running until the Pi's battery power runs out. And then inside that, we've got a couple more loops which accomplish what it says here. We're going to flash the LED 5 times every 30 seconds, and then every 5 minutes, write the uptime of the Pi to the spreadsheet. So we've basically got a couple of counters going on here called counter AA and a counter BB. The inner loop here basically says, well, counter BB is less than 5, turn the LED on for half a second, off for half a second, add to the counter, keep going round until that's happened 5 times, that flashes the LED. And then the outer loop here is going to run 10 times over. It'll run the inner loop. It'll then wait for 25 seconds, which will give us a total time here of 30 seconds. It'll then increment the counter and we'll run the whole thing there for 5 minutes across this whole outer loop. We're then going to calculate the current uptime for the Pi. Uptime is going to be the current time minus the start time. That'll give us a figure in seconds. So if we divide by 3,600 or 60 times 60, we'll get a figure in hours. And then we're going to add that data to the spreadsheet, as you can see. And then finally, we're going to save the spreadsheet, first of all to where it's initially located in document, but we're also going to save a second copy to a backup directory because we know the Pi is not going to close down neatly. It's going to close down by having its battery power running out, and therefore that might corrupt a file open at the time, and therefore I think I've got less chance of having a corrupted spreadsheet if I save 2 copies in different locations. To make all this work with the Pi running headlessly, I need the Pi to auto-run this code, and I'm achieving that with a little bash script over here, which basically runs that piece of code, and that is put into the Pi's auto-start file. It's relatively tricky getting a Pi auto-starting. I have covered how you do it though in other videos, so I won't go into too much detail of how I'm achieving it right here. Anyway, that's what we're doing, so let's set things up to run our first test, and here we are with the power bank and the Pi, and I've discovered that whilst this power bank does have an on-off switch, it very, very annoyingly auto-activates the first time you plug something in, which I find intensely annoying, but there we are. That's what it does. But the Pi 3A Plus is now booting up, and hopefully in a second, we'll maybe just speed on through to get to the point. There we are. Its LED is flashing. Hopefully you can see that on camera, and the test has started. And so this will now run for many, many hours until the Pi runs out of power, and then we can look at its spreadsheet and see how long the battery lasted. And here we are some considerable time later. The power bank has been exhausted, and I've rebooted the Pi 3A Plus with a power adapter. And if we go into LibreOffice Calc, we can look at the spreadsheet. This is very exciting. I've not looked at this yet. I'm assuming everything is okay because the Pi booted up again, so we didn't corrupt the microSD card when the Pi ran out of battery power. But there's our spreadsheet. And yes, all of these uptime figures are there. And if we keep scrolling on down, as we can hopefully see, when did it finish? There we are. The final uptime recorded was 27.74 hours. So that's how long the Pi 3A Plus lasted running on the power bank. So I'm now going to repeat the test on the Raspberry Pi 4, which I put in a heatsink case, as you can see. And well, we've got some results here. In fact, the first spreadsheet, the one in documents, did get corrupted, but the one in backup didn't. And as you can see, we've got a final result of 15 hours for the Raspberry Pi 4 on the power bank. So let's now repeat the test for the Raspberry Pi Zero, which I put in a Pibo case. And here I am a few days later with a spreadsheet of results for the Raspberry Pi Zero. And if I scroll on down, frantically going down on the scroll wheel here, the Pi Zero struggles a bit running LibreOffice Calc and a spreadsheet of any size, but as you can see, we've got results, and hopefully in a second you'll see there we are, almost went past it, an uptime of 58.5 hours running our minimal load test on the 10,000 milliamp hour power bank. So let's put all of our results onto the table, where we can see that the Pi 4 and Pi 3A Plus have performed ahead of expectations, while the Pi Zero ran fewer hours than I predicted. And my guess of what's going on here is that the Pi 4 and Pi 3A Plus are using less power in my minimal load test than the typical bareboard figure provided by the Raspberry Pi Foundation, and that the usable capacity of the power bank is less with a very low current draw, so reducing the runtime of the Raspberry Pi Zero. And as you probably noticed, I've decided not to test the Raspberry Pi 3B Plus and the Raspberry Pi Zero W, purely because if I did so, this video could still be in production when the universe comes to an end. Right, we're now going to test out a rechargeable lead acid battery, and specifically this NP7 12-volt model, which I purchased for £17.99, with similar batteries priced from about $24 in the United States. And I also purchased this little charger so I could charge it up. This charged it in about 12 hours. Now, as you probably know, 12-volt batteries are very common indeed, 12-volt lead-acid batteries, because they're used in cars and boats and things like that, and therefore, over the years, many people have asked me about running a Raspberry Pi on a battery like this. And to make it work, we need to convert the 12-volt power we get out of the battery down to 5 volts for a Raspberry Pi. And here I'm going to do that using this, which is a packet of magic beans. No, it isn't a packet of magic beans, it's a buck converter. And if we bring in Mr. Scissors, here he is, he can get us into this little packet like that, there we are. Get out the buck converter, and as you can see, this is a rather handy little unit. Let's give you a closer shot of it. And I purchased this for £5.99. It's rated at 5 amps. And it accepts 12-volt input at this end using either a barrel jack or terminals, and it outputs 5 volts at the other end using either terminals or a Type A USB connector. And the big advantage of using a buck converter like this to do our power conversion is that buck converters are very efficient indeed. It's about 90% efficient when you convert power from one voltage to the other using a buck converter. Returning to our NP7, we can see that its rated capacity is 7 amp hours, which is 7,000 milliamp hours at 12 volts. So stepping down to 5 volts using our buck converter will give us a rated capacity at 5 volts of 7,000 times 12 divided by 5 and multiplied by 0.9 to account for the 90% efficiency of the buck converter, which gives us a final figure of 15,120 milliamp hours. However, as previously with our USB power bank, a lead-acid battery's usable capacity will be considerably less than its rated capacity, and it can indeed be down to just 50% of what the battery is rated at. However, a 50% usable capacity for a lead-acid battery is typically in situations with a very high current drain, which will not be the case when we're using this to power a Raspberry Pi. And so here I'm going to assume a usable capacity of 65%, which gives us a final figure of 9,828 milliamp hours at 5 volts. So, if we go across to another table that reminds us of a typical bareboard power drain of different Pi models, we can calculate theoretical bareboard battery life expectancies as in this second row. However, as previously with our power bank, what we really want are some actual test results. And so, we'll now connect up the MP7 and buck converter to our Raspberry Pi 4 and start our minimal load battery life test. And here I am back again many hours later with a spreadsheet of test results for the Raspberry Pi 4, and these results are bemusing me because, as you'll see if I scroll down, I have to keep scrolling a very long way because the Pi 4 ran for an extraordinary amount of time on the lead-acid battery. There we are, a total uptime of 40.1 hours if we round to one decimal place, which is massively more than I anticipated, over twice what I calculated. And I guess we know from the power bank test that the Raspberry Pi 4 is using less current in my test here than in the Raspberry Pi Foundation's bareboard notional figure. And it has to be the case that our lead-acid battery has got a significantly greater usable capacity than 65% running on a low current drain as we've got in this test. But even so, this is a spectacular result. Anyway, I think I'm now going to move on to test out the Raspberry Pi 3A+ on the lead-acid battery, and I'll come back to you in a few days, during which time I'm sure I'll be musing on the Raspberry Pi 4 result. And here we are with the results of the Raspberry Pi 3A+ on the lead-acid battery. It has run a considerable period of time. We get to the end here, you'll see, there we are, it's run just over 3 days, 72.1 hours. And so, without further ado, we'll move on to our final test, the Raspberry Pi Zero on the lead-acid battery, a test which will take the best part of a week to conduct. And here I am back again with the Raspberry Pi Zero's lead-acid battery test results. And guess what? I was wrong. The test ran for more than a week. It wouldn't complete in a whole week. Some extraordinary results here. I'm scrolling down on the Pi Zero, trying to get to the bottom without losing everything off the screen, almost getting down there. Let's slow down a little bit and show you the final result. Guess what it is? I'm as amazed at these results as hopefully some of you are as well. The final result is here, and it is, look, 187 hours. I'm staggered we've managed to run the Raspberry Pi Zero for well over a week on one charge of battery. But I'm also equally staggered that the Raspberry Pi Zero has remained stable over that period of time to be writing a result to a spreadsheet every 5 minutes for an extraordinary number of hours. So let's put this result into our lead-acid battery test table, and we can see there again massively exceeding our expectations of what the results would be. And let's also now put the results into a table where we can see the results from both the power bank and lead-acid battery tests. And we could draw all sorts of conclusions from this data, but I will highlight just two things here. Firstly, I think I've proved the importance of running real-world battery life tests. And secondly, running these tests has given me a renewed respect for lead-acid battery technology. These days, we spend a lot of time using devices that use lithium-ion or lithium polymer batteries, which are small, they're lightweight, they charge quickly. Lead-acid batteries are large and very heavy and may charge very slowly, but as we can see here, performance from lead-acid really can be very good indeed. And given that the batteries I've been testing are about the same price, it is clear if you want to get the best battery life for what you're paying, it's certainly worth considering a lead-acid battery to power a Raspberry Pi. Running a Raspberry Pi on batteries opens up all kinds of possibilities for mobile and remote applications. And indeed, in my next Raspberry Pi projects video, I'm going to be putting a Raspberry Pi into my greenhouse so that it can water the plants. And that greenhouse is distant from mains power, and so the Pi will be running on the lead acid battery we've looked at in this video. But now that's it for this video. If you've enjoyed what you've seen here, please press that like button. If you haven't subscribed, please subscribe, and I hope to talk to you again very soon.